isentropic temperature at the exit of the turbine, and you have also the total pressure, okay? So I remind you, the isentropic efficiency of the turbine, this is minus TT4 minus TT4i in the denominator, and here this is for the compressor TT2i divided by the TT2. Why do I mention that? This is because we need to understand what to do with this. What is the explanation behind this PT4? What will we do with that? Why is this parameter so important? In fact, it's interesting to go on a TS or HS diagram. Total temperature entropy. Which temperature, which enthalpy? Let's say first that we speak in total elements, because you see that we start from a total temperature and a total pressure. What is the situation? We start from PTA, okay? PTA is a value higher than PA, and we can indicate that we have, let's say, a point that is here, that is at a PA lower than PTA. It depends, of course, the flight speed and so on. So, but let's say that there is a certain distance. I don't take a too large one, otherwise I will not be able to give a drawing of my system. And these points are, of course, let's say like this, and I have one point there. This is the point A, corresponding with PA and TA, and this is the point A total, this one, that is corresponding with PTA and TTA for a given value of the entropy that we have at this moment. And what will I do with this? I will go into the intake. The intake is with TT1 that is equal to TTA. So I'm staying on an horizontal line, and this is an horizontal line, and I'm going to a PT1 that is smaller than the PTA, and of course with an increase of the entropy. So this is the point 1T that is at the entrance of the compressor. And you see that you could also try to look at what is the value of P1 and the value of T1 by considering that you have TT1 is equal to TTA, and that we know the new PT1, and depending on the M1 that you are considering, let's say you take M1 equal to 0.5, 0.55 as an assumption, or you know better values, and you can characterize also the point 1 static, but it's not easy to represent this point 1 static there. The only thing you can say that this will be on a vertical line here with the same entropy, of course. And then you go into the compressor. So you start from this point, and you can go into the compressor isentropically. So you would have the point 2i. You're arriving on PT2, that is here. And if you are not changing isentropically, you would arrive in the point 2, that is here, with here the TT2i, and here with the value TT2. So you see, TT2 is higher than TT2i. So TT2 is here and TT2i is there. Isentropic efficiency is lower than 1. Okay? This is for a certain pressure ratio. And then you are entering into the combustion chamber. What's happening into the combustion chamber? You will have a decrease of the total pressure, and you will have a huge increase of the temperature arriving here. So this is the TT3 that we have also called the TIT. And you inject here the fuel flow multiplied by QCI multiplied by eta Cc. And you are here in the point 3. And there you are going into the turbine. You see that the expansion in the turbine, this is something that can be isentropic or real. And we have a, let's say, rather small expansion because there is no load. The only load is, let's say, the compressor plus some accessories. So the expansion in the turbine is much lower than in the basic gas turbine cycle, much lower than in the turboshaft in this cycle. This cycle, I call that a turbojet. I have not yet mentioned this name. The expansion in the turbine is much lower in the turbojet than in a turboshaft and then in the basic gas turbine cycle. So I stop much before, let's say I stop here, with the PT4 that I have computed there, and with here my point 4i, that will fix my TT4i, and here my point 4, that is fixing my TT4 higher than TT4i. TT4 higher than TT4i, so TT3 minus TT4 smaller than TT3 minus TT4i. Okay? Question, what do I need to do now? So the first thing to observe is that this TT4 is a very high temperature because we have increased a lot the temperature in the combustion chamber, and I have had a small expansion in the turbine, and TT4 is the real temperature, higher than the isentropic one. So TT4 is a high temperature, I would even say a very high temperature, let's say 800 Celsius, 900 Celsius, 1000 Celsius, very, very high temperature that we have at the exit of the turbine. And I'm entering here from this point, this is from this point that I'm making the rational, I'm entering here into the exhaust nozzle. The exhaust nozzle can be also isentropic or it can be non-isentropic. I will not make really the difference. I will consider the nozzle, the exhaust nozzle, as isentropic, but I will not exactly introduce an isentropic efficiency of the exhaust nozzle. This is a parameter that I will not really consider. It's not making a large difference. It would only complexify the situation, and I'm not introducing an isentropic efficiency of the nozzle, what I could do, but I will not do that. So I will follow this path, but in fact, I'm not making really the difference, and I will consider that the exhaust nozzle is isentropic. If you want, I'm not really insisting on this difference in the nodes and in the computations that we will do. But the question is, what will I compute in this exhaust nozzle. I know PT4 and I know TT4. I know also m dot plus m dot f, which is the total mass of gas at the entrance of this nozzle. And what is happening in this nozzle? The nozzle that I'm considering is the simplest nozzle that we can imagine. We will see if it's not enough, but there is no reason not to consider the easiest nozzle that is possible, which is a pure converging nozzle. A pure converging nozzle. So I will consider, as I said to you, that PT is a constant. It's not very important, even if in reality this is approximately right. I will consider that TT is a constant. This is fully right. So between the section 4 and the section 5, I have constant PT, constant TT. If you would say that PT is a bit lower, you take PT5 is 98% of PT4 is not changing the problem. It's very easy to implement, but it's not necessary to do. And what's happening? I have a subsonic flow. M4 is for sure lower than 1. And M4 is maybe known by experiments or maybe not known. It's not changing too much the situation because what I will need, this is just to know the total pressure that I have computed and the total temperature, the real one that I have computed. And what's happening in a nozzle like this one? It's a convergent. So what's happening in a subsonic convergent nozzle? The Mach number is increasing, the speed is also increasing, total temperature is constant, total pressure is slightly decreasing, but we say it's constant, and we will have the static pressure and the static temperature that will decrease. They will decrease because total temperature is constant, Mach is increasing, static temperature is decreasing. This is about constant, this is increasing, so the static pressure is decreasing. So what's happening? Mach number is increasing, static pressure is decreasing. Static pressure is decreasing. What are the limits? What are the limits? I have created an exhaust nozzle with a smaller geometry, smaller area, smaller section at the exit compared to the intake. So I have introduced a throat, a minimum section. And in a throat, the maximum Mach number in the throat, which is also the M5 maximum, this is 1. I cannot go higher than 1 in a throat like the one I have drawn. But there is another limit. The other limit is that here outside I have the atmospheric pressure.